mini lecture, we're going to talk about the derivative as a function. So we've been looking at in the past how we considered the derivative of a function f at a fixed number a, and then using the formula f prime of a equals the limit as h approaches 0 of f of a plus h minus f of a over h. So now we start to change our point of view and let the number a, we let that a vary. And then we substituted a in the equation at the top. Instead of using a, we're going to use the variable x and then use the equation at the bottom. And then we get here f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. So given any number x for which this limit will exist, then we assign to x the number f prime of x. So we can think of f prime as a new function called the derivative of f, and then it's defined by this bottom equation. We know that f prime at x, right, f prime of x, we already know that this can be interpreted as, in a geometrical sense, what we've been talking about before, the slope of the tangent line to the graph of f at that point being x comma f of x, right? It's geometrically interpreted as the slope of the tangent line to the graph of the function at the point x comma f of x. So now if we take a look at the graph of a function, some function f right here, it's given by this figure. So we're going to use the graph of this function to sketch the graph of the derivative f prime. So we're given f. Now we're going to use this to sketch f prime. So using this graph, let's go ahead and estimate the value of the derivative at each of these values of x by drawing a tangent at that point x comma f of x. So it looks to be right here, right? Tangent right there, tangent right there, and going to be a tangent right there. Okay, so we'll call that A, B, C, and we'll just call this one point P. So here we have slope being 0, right? Horizontal line, slope being 0 there, slope being 0 there. Here we can just estimate the value. So we'll just say the slope is about 3/2 right there. So that's about 1.5. So now if we want to plot some points, let's gather some points together. So for point P, we're going to have, and I should have labeled it a little bit more. Let's go ahead and label this. This is at 5 right there. 4, and then C is about at 3. 2, and then the 1 is already listed. So P will be at 5, comma, we said 3.5 is what we estimated it at. So that's 5, comma 1.5. All right, and then C is 3, comma 0. And then the next one, B. B is probably between 1 and 2. So I would say that's like 1.5 and then 0. 0 is our f of x. And then A is about at 0.5, comma, again we have a 0. Notice we have 0 slopes. Okay, so these are all the points that we've obtained from all of these x values, 0.5, 1.5, 3, and 5, and the slopes of their tangent lines at those points, at those x values. So we can just take those and now we can plot these points. So for instance, the P5 comma 1.5 is right there, 3 comma 0, and 1.5 comma 0, as well as 0.5 comma 0, right? So we see all of those points are now plotted. So this is now on the graph of f prime. F prime, the derivative, the graph of the derivative. So we took those points that we found and now just plotted them on a new graph. So if you noticed, which I'm sure you did, that the tangents at A, B, and C, right, at A, B, and C, those tangents are horizontal, so the derivative of 0 right there at those points. And the graph of f prime crosses the x-axis. See how it crosses the x-axis? Crosses the x-axis at the points A prime, B prime, and C prime, directly beneath A, B, and C. So between A and B, right, if we look closely between A and B, I'll highlight this. Between A and B, the tangents have positive slope. Prime is positive there, right? Positive here. It has a positive slope, so it's positive. Reference it from the graph above. So once again, between A and B has a positive slope. So therefore, on f prime, it's positive there as well. Now let's look at up top at the graph at above between B and C. Between B and C. Right here, between B and C. See how that slope is a negative slope of that line between B and C? So therefore, between B and C, that's going to be negative. Sorry, that's going to be negative. All of that is a negative. So see how that relationship? So let's take a look at some other notations. So if we use the traditional notation, y equals f of x, right? We use that traditional notation, y equals f of x. And this just indicates that, as you know, the independent variable is x, the dependent variable is y. And then we'll have some alternative notations for the derivative, right? As we already know, being f prime of x, we could say y prime. We could also say dy dx, which is just saying the derivative of y with respect to x. Df dx. I'll continue down below. I want to go straight across, but it's fine. We could say derivative of f of x with respect to x, so df of x dx. Also, there's capital D f x, and then we'll also maybe see something like this, capital D with x as a subscript, f of x right next to it, f of x like that. So alternative notations that you may see for the derivative, right? So that capital D that you see, or the D, the capital D, or the d dx, these are known as differentiation operators, differentiation operators, because they indicate the operation of differentiation, which is just the process, as we know, of calculating a derivative. So that symbol dy dx, pretty popular, introduced by Leibniz, and make sure you know that it's not a ratio, right? It's not a ratio. It's just another way to use f prime of x, the derivative. So we can actually rewrite the definition of a derivative in Leibniz notation, right, in the form of this being equal to the limit as delta x approaches 0 of delta y over delta x.